All right, let's get started. So, hello everyone, and today we are gonna probably finish our section on indexes. The last time we have been talking about tree index structures, which essentially correspond to a search tree. And this time we're gonna talk about a different type of indexes, which is based on hash functions. Trying to advance my slide here. All right, so here we have again this architecture of database management systems. So we are currently still discussing about how the data is laid out in order to make it efficient to access. And we're also talking about the data access component in the storage manager. For hash indexes, the relevant chapter in the Ramakrishnan and Gerke book, that is the number 10. And so far, we have been discussing about those tree indexes, where you essentially traverse the tree from the root node to one of the leaf nodes in order to find interesting entries. For the hash function, it works a bit differently. If you're looking for one specific key with your index, then you first evaluate the hash function on that key. And then depending on the outcome, you know which bucket to look for. And with that bucket, you have a page associated. On that page, you find the entries that you're looking for. High-level picture, we're going to see it in more detail in the following. Now, let's first of all discuss a little bit about the types of predicates that those different indexes can support. Now, tree indexes are fundamentally based on a comparison between keys. So if you think, for instance, about the leaf nodes of an index tree, then the entries in the leaf nodes are sorted by the key. That means that keys, like entries for the same key, are stored close together. It also means that entries with similar keys are stored close together. And because of that, I can exploit those tree indexes quite conveniently in order to treat inequality conditions. Just need to scan some range in the leaf nodes, and there I will find all those entries with similar keys stored together. Also, we have seen that we can use tree indexes with composite keys. And if I sort keys by composite, if the key is a composite of multiple columns, then it means that those entries which have the same or similar values in a prefix of the key columns, they are still stored close together. And that is why I can use those tree indexes also in order to treat predicates that refer to a prefix of the composite key columns. Now let's see how that works for hash indexes. Now hash indexes are based on hash values. That makes them useful for equality conditions, because if two entries have the same key, then the hash value is also exactly the same, and that means they will be stored in the same bucket. Now, on the other side, if two keys are similar, close together, it does definitely not mean that their hash values are close together in any way. And that means that they will probably be stored in different hash buckets, even if their key values are relatively close. And since similar keys are not stored close together, it makes it inefficient to try to use hash indexes for inequality predicates. Also, if you have composite keys, then if you have the same value in a key prefix when comparing two entries, it does not mean that they will be stored in the same hash bucket. Most likely, they will be stored in different hash buckets. And this is why you typically want to use hash indexes only if you have conditions on all the columns of the composite key. So in a way, hash indexes are a little bit more restrictive in terms of the predicates that you can use them for when comparing to tree indexes. Now in the following, we're going to see a couple of different hash indexes. We are going to see 3 different variants. This is a high-level overview. In the following, we're going to go into detail. We are going to start by looking at something called static hashing. And as the name already indicates, it's not a good idea if you have very dynamic data with lots of insertions and deletions. In those cases, you probably want to use something like extendable hashing. Now, this one has one drawback, which is that if you keep inserting data, then every once in a while, you need to perform one expensive operation in order to update the index. And we will see later precisely what that operation is. Then we have something called linear hashing. And this one has the advantage over extendable hashing that it extends the index very smoothly without costly operations. It has a couple of other drawbacks, but we're going to discuss them in detail in the following. So those are the hash indexing variants that we will look at in the following. Static hashing is perhaps the simplest one among those variants. Essentially, you have pages associated with hash buckets, and they store the references to the data. Or what is also possible, like in the case of tree indexes, you might even store the data just directly. Now, the hash bucket pages, they are associated with specific value ranges. So the way you use one of those indexes when looking for entries with a specific key value is that you first of all calculate the hash value for that key you're looking for. And then you look up the bucket page which is associated with the hash value. This is a little illustration here. Again, we are storing entries about students. And on the left-hand side of the screen, you have the hash function, which associates specific student names with a hash value. Just to make sure, this hash function is not explicitly stored as a table. You only calculate it based on the bits that are directly available in the key. I'm just putting the hash function here for convenience, but it is not actually stored anywhere in your database. What is stored in your database? That are those pages that you see in the middle of the screen here, page 0 to page 3. And here we use the simple system that the page ID corresponds to the hash value modulo, that's what the percentage sign symbolizes, modulo the number of buckets. So for instance, if you want to store student Alan, you look up in the hash function, okay, Alan would have a hash value of 1, and 1 modulo the number of buckets, which is 4 here, that would still be 1. So we will store Alan in page number 1, and this is indeed where you can find him. Or Bob, for instance, has hash value of 0. So here we store it on page number 0. Let's maybe have a look at one more. Dora has a hash value 5, and 5 modulo number of buckets, which is 4, is 1. This is why we would store her on page number 1, but we actually haven't stored her anyway. So the hash function here, it gives you the hash values for all the students that we will consider in the following examples. Here, in this example, we have only inserted a subset of students. So let's maybe see one more. For instance, okay. For instance, salmon. So this one has a hash value of 4, and 4 modulo 4 is 0 again. This is why we store him on page 0, as you see here. So that is pretty intuitive. You calculate a hash value, and then you look up the associated bucket page. And there you find your entry if it exists in the index at all. Now, let's see how those indexes change if we change the data, because the index always has to refer to the actual data. So if the data changes, then you must also change the index. Now, deletions are relatively easy. you just remove the associated entries from their associated pages. That always works. And I think there might be a question in the chat. What are keys with the same prefix? So that question refers to the composite keys, I imagine. We have discussed about an example last time, for instance, where we have one index, one composite index that allows you to efficiently retrieve customers in specific zip codes that have bought one specific product. So you have essentially conditions on two columns, and your index can use both columns as a search key. But if you have one of those composite search keys, then with tree indexes, you have to choose an order between the different components of the composite index. And if you want to use the tree index, you can only do that if your predicates refer to a prefix of the composite key columns. So for instance, if you have indexed first by zip code and second by a product, then you can use that index in order to answer an equality on the zip code, but you cannot use that index to answer an equality on the product alone. You can only use it for predicates that restrict prefixes of the composite key. All right, sure. Okay, and back to the hash indexes. So we have discussed that deletions are relatively easy to do because it just removes the associated entry. Insertions are a little bit more difficult because maybe the page on which you would insert an entry is already full. So we have something which we call a page overflow. Now, in those cases, you somehow need to add additional pages to the index clearly. And you can do this using so-called overflow pages, which we have already seen in the case of tree indexes. So this is a very similar principle. Now, so the initial bucket page essentially stores a pointer to the first overflow page on which you have stored entries after insertion. And if you keep inserting entries, you might even need multiple overflow pages. So in that case, the first overflow page would store a pointer to the second overflow page. The second overflow page stores a pointer to the third one, and so on. So you will get a linked list of overflow pages in the end. At some point, that becomes inconvenient with so many overflow pages. So what you can do at this point is that you just essentially recreate the entire index from scratch. You rehash every entry that you have in your index, and then you can avoid overflow pages again. But that, of course, is an expensive operation. And while you're reorganizing your index, your database may not be able to accept the new input, which is very inconvenient. All right. And here is one question, very strictly speaking. The hash bucket, that is essentially some range of hash values, and then there is a page which is associated with that range of hash values. So they are linked, very strictly speaking. There's a subtle difference. All right. Now, this is an illustration of those overflow pages. Here you see we have expanded the index that we have seen in the last example. We have inserted more entries, and obviously we didn't have enough space anymore for those entries. This is why we needed to add overflow pages. And you see those overflow pages P101, 105, and P107 on the bottom of the screen. Those red arrows indicate pointers that are actually stored on those original pages, and they link to the first overflow page. If you would have multiple overflow pages, then they would form a linked list for the same hash bucket. So if you analyze the pros and cons of those hash indexes, then clearly what is good is that you can data with one single page read, at least as long as you don't have overflow pages. If you remember, for the tree indexes, in order to find the entries that we were looking for, we typically had to look at multiple pages, starting from a root node, then one node in each of those tree levels. So in a way, those hash indexes, if you calculate the hash function, you know which page to look at, so that can be very efficient. On the other side, of course, with static hashing, if you have overflow pages, then you might have to look on multiple overflow pages to find the entries that you're looking for, or in order to conclude that the entry you're looking for is actually not present in the index. In any case, you would have to look at multiple pages, and that is bad for performance. We also have said that deletions are easy because I can just take out the entries. But of course, it means that at some point, I might have lots of empty pages. That was already a problem that we quickly discussed in the context of the static tree indexes that we have seen. So if you delete more and more data, at some point you will be wasting space because you have lots of pages in your index that are either empty or is near to empty. What you can always do is that you rehash everything, you recreate your index from scratch, but as discussed, that is quite expensive. Now, an alternative which works better for dynamic data is a so-called extendable hashing. And here the idea is that we introduce one new level of indirection. We introduce a directory which links a specific hash buckets to specific pages. So instead of calculating the hash value and then directly looking up the corresponding page, you would calculate the hash value, then you would look up in the directory which page is associated with that one, and then you would look up the corresponding page. Now, what it gives us, this directory, is essentially more flexibility about how I handle situations in which I need to add pages to the index. So essentially, if I have one specific page that is overflowing, then I introduce a new page and I rehash the entries that were on the original page together with the new entry that I'm currently inserting in order to balance those entries just across those two pages. As I'm adding more pages, every once in a while, I need to increase the size of the directory. And then can be a little bit expensive, but in each case, it is much cheaper than having to rehash, having to recreate the entire index from scratch, which is what static hashing has to do. Let's make things a little bit more concrete by an example. So in this example, I have extendable hashing, and on the top of the page, you see the directory pages. Right now, that's only a single one, page 120. And on the bottom of the screen, you see the bucket pages, page 131. Now, right now, we only have one single page that stores data entries, which is page 131. So the directory only has one single entry. Here on the left-hand side, you essentially see the hash values that we are associating with a page. And in the right column, you see the corresponding page that we are referencing. And to make the following easier to follow, here for the moment I have written the hash values in the hash function according to the normal system. But now let's actually switch and write those hash values in the binary system, because it will make the following examples more convenient to represent. So here we had the hash values between 0 and 7. That means I need 3 bits in order to represent that. And right now in the directory, you see on the left column, we have those 3 stars. And by that, I mean that here we are associating all entries independently of their values for those 3 bits of the hash function with page number 131. Now we have just inserted student Alan into the index, which you see on the bottom of the page. Now let's insert a student Bob next. All right, so here nothing much happens. We insert Bob on page number 131, which is the page associated with all hash values as indicated by the directory ****. So we can have any values for the hash bits. All right, now let's just insert the next student in alphabetical order, which is Chen. And again, we can insert the student here on page 131. Now it becomes interesting because if we insert the next student, Dora, we don't have enough space anymore on page 131. That means we need to introduce a new page, but we don't want to introduce an overflow page. So we need to add an associated entry to the new page in the directory. So now let's do this. And here you see on the bottom, I've introduced a new page 133. And in the directory, I have introduced a new entry. So and now we have two entries. So we somehow have to associate them with non-overlapping value ranges of the hash function. So here we say that page number 131 is associated with all entries whose hash value ends with a 0, and page 133 is associated with all entries whose hash value ends with a 1. And here on those pages 131 and 133, I have distributed the entries accordingly. I needed to distribute the old entries on page 131 and the new entry, student Dora, that I have just inserted. And you see, for instance, Bob has a hash value of 000, so it ends with a 0, and that means we put it on page 131, while Alan has a hash value of 001. So we have to put it into page number 133. All right, so let's insert David. And David has a hash value of 001, so it ends with a 1, and we should insert it according to the directory into page number 133. All right, now next student is would be Esther. And if we insert Esther, then something interesting happens, because Esther, the hash value ends with a 1, and it would need to go into 133. But that page is already full, so I have to add more pages. If I add more pages, I again need to assign them to non-overlapping value ranges in the directory. So far in the directory, I have only considered one single bit, the last bit. And that was sufficient in order to distinguish two different pages. But now if I add a third page, then like 1 bit is not sufficient anymore to distinguish between 3 pages. So that is why the directory will need to consider 2 bits now. So let's do this. So we are adding one new page. We quickly move the chat so I can recognize the page number. And that page is 139. And in the directory, we have expanded the directory, because now we need to consider the last 2 bits instead of only the last bit. And as you see here, I'm associating those different pages with non-overlapping value ranges. Now, one interesting thing here happened. So the new student that I wanted to insert, Esther, would have to be inserted in page number 133. So this specific page was overflowing with entries, and that's why I actually only wanted to split that specific page. On the other side, page number 131, that one still has some space available and it is not overflowing. This is why we have not split page number 131. And if you look at the directory, you see that essentially all the hash values ending with 00 and all the hash values ending with 10, they are both assigned to the same page number 131. Eventually, once we add more entries, then we probably need to split 131 as well, and then those entries in the directory change. But for the moment, there's like 2 entries in the directory that point to the same bucket page. All right. So let's insert a few more students. It's the same principle. Now we've inserted Felix, and now we are inserting Gerd. And Gerd has a hash value 010. So that means it would have to be inserted into page number 131. But now that page is also overflowing, so we need to split it into 2 pages. And we are doing this by adding one more page in the bucket pages and redistributing the corresponding entries. And as you see here, now we have updated the directory, and page 131 only has 1 entry left. The other entries have moved to page 126. So, and now we can insert a little bit more, and at some point we have too many bucket pages to index them with 2 bits alone. So at that point, I need to expand the directory further in order to consider all 3 bits of the hash function. And if that happens, I also have to increase the size of the directory. And as you see here, now the directory considers all bits from the hash function. There is some pages that are linked to repeatedly in the directory, for instance, page number 131 again, and there's other pages that are linked to only once, depending on how many insertions we had for the corresponding range of hash values. So this approach is pretty flexible. I encourage you to have another look at this example. But the main point really is that we have this directory which associates hash value ranges with specific pages. And having this directory gives us a lot of flexibility in order to only split those specific buckets that are currently overflowing. Now, here you have a little summary of this insertion algorithm that we have already executed so far. So the way it works is that you always start by first calculating the hash value for the new entry that you're currently trying to insert. Then you look into the directory in order to identify the associated page. And if that page still has some space, great. We simply insert the new entry, no problem. If the page is currently overflowing, it cannot store the new entry anymore, then it becomes more interesting. We always have to add a new bucket page, and we have to redistribute the entries on the page that is currently overflowing and the new entry on those 2 pages. In order to redistribute them between those 2 pages, I consider one more bit from the hash function. And if needed, I might have to expand the directory if currently the directory considers less bits than what I have used in order to redistribute the entries after the insertion. There's some terminology that is often used in the context of those extendable hash indexes. You also find it in the book. So I wanted to quickly link this description to that terminology. So we always have discussed about the number of bits that are considered in specific cases. Often people say that global Dept, this is the number of bits from the hash function that the directory currently considers. And the local Dept for one of those hash bucket pages, that is the number of bits that you need to consider in order to be sure that an entry is located on that page. So let's quickly make that a little bit more concrete by the example. For instance, here, this is the state that we finished in. And in the directory, you see that we have a global depth of 3 because the directory is currently considering 3 bits. On the other side, you have different local depths for the different bucket pages. For instance, take page number 131. So this page is referenced twice in the directory on the first directory page and on the third directory page. I actually just spotted that we have like multiple directory pages with the same page ID, which should not be. So you should have different pages, of course. That's a little typo. But we see that we have a page number 131 linked to twice in the directory, once for the hash values 000 and once for the hash values 100. That means whenever you know that the last 2 bits of the hash function are 00, you can be sure that the corresponding entries are associated with page number 131. So in order to know that page number 131 is interesting to you, you only need to consider 2 bits, and that is why the local depth for page number 131 is 2. On the other side, if you are taking page 133, for instance, then that page is only linked to once in the directory. And that means that in order to be sure that this is the interesting page for the entries you're looking for, you have to consider all 3 bits from the hash function. And that is why the local depth for page number 133 is 3, because you have to consider 3 bits in order to be sure. All right. Now, this is how insertions are handled. And maybe one last word on global versus local depth. You can say that the condition which causes you to expand the directory, that is always if the local depth becomes greater than the global depth. So the global depth of the directory must always be an upper bound on the local depth of all of your bucket pages. That is one way in which this terminology becomes useful. All right. So now we have discussed about insertions into those extendable hash indexes. Now what about deletions? Clearly, if we have enough deletions, then we could merge together again some of those bucket pages if the number of entries on them is low enough in order to fit on one single page. At some point, if I keep merging pages and the number of pages therefore shrinks, I might even be able to reduce the size of the directory. In practice, however, people often assume that insertions are more common than deletions. And so the implementations that you find in practice, they might often not do anything sophisticated in case of deletions. But handling insertions well, that is pretty important. Now, if we analyze the pros and cons of that index, so a first pro, of course, is that we avoid overflow pages. And on the other side, we don't need any expensive rehashing. So when we redistribute entries, it's always only the entries on one of my pages. So that means quite reasonable overheads. On the other side, of course, I'm introducing a directory. So I need one additional access in order to look up things in the directory. And every once in a while, and that is more important, I need to double the size of my directory if the local depth exceeds the global depth. Now, doing this operation where I double the size of the directory, that takes some time, which is inconvenient. Of course, it is much faster than having to recreate the entire index from scratch, which is what static hashing might do. But nevertheless, it is a little bit inconvenient. So the idea of the next hash index method that we will consider is to avoid this occasional overhead of having to double the size of the directory. Maybe one last question before we switch to the next hashing index. On the last slide, I wrote that we can avoid overflow pages, at least often. The question is, can we always avoid overflow pages with that kind of index? Or is there situations where we cannot avoid them perhaps? Okay, yes. And I already see the right answer here in the chat. Very good. Exactly. So the thing is that hash values are generally not unique. So you might have a hash collision where multiple entries map to the same hash value. And in those cases, there is no number of bits that you could consider in order to separate entries from each other. Then you might not have another choice than to use overflow pages. Of course, you might wonder, maybe if I use a different hash function, I wouldn't have that problem. But in the end, you might even have like multiple entries for the same key. If you think about the enrollment table, where we might have multiple entries for the same student. And if you have too many entries with exactly the same key, then even the best hash function, of course, will not help you anymore. And then you actually have to work with overflow pages. Very good. All right, let's continue with so-called linear hashing. So that is the last hash index method that we will see. So the idea here is that we essentially get rid of the directory again. Now, in a way, it is the directory that gave us the flexibility to choose which specific pages, which specific buckets we wanted to split after insertions. So if I get rid of the directory, then it means I also have to give up some flexibility in choosing which buckets I split next, because I don't have a directory anymore to keep track of that. So what I do, therefore, is that we are selecting buckets to split according to a round-robin principle. And in particular, that means that I might not even be able to immediately split one of those buckets that are currently overflowing. So that can seem inefficient, and it sometimes is. You have bucket number 5 is overflowing, but the next bucket that you have to split is bucket number 1. That might be currently almost empty. So nevertheless, since you are fixed to one specific order in which you need to split the buckets, it means that you would have to split bucket number 1, and you would have to introduce an overflow page for bucket number 5. Of course, eventually, if you keep splitting buckets, then after a while, you will reach bucket number 5, and then you will probably be able to get rid of the associated overflow page. But at least temporarily, you will have to allow for some overflow pages. But typically, they don't persist for very long. So that is the high-level idea behind linear hashing. Now let's see a little illustration for how that works. So generally, splitting proceeds in so-called rounds. And on the left lower corner of the slide, you see the round counter. A round essentially ends once you have split all the buckets that existed at the beginning of the round. And you see there's a big red pointer pointing to the bucket that will be split next. After a round is finished, we will reset that pointer to the first bucket again, and then the next round starts. So right now, we only have one single bucket that exists at the beginning of the round. And those 3 stars here mean again that this page here is supposed to contain all the entries for any value of those 3 hash bits. All right, so now let's assume that we have insertions, and therefore we need to split this bucket over here. So now we are splitting this bucket, and we are splitting it into 2 buckets, one of them associated with hash values where the last digit is 0, and one associated with hash values where the last bit is 1. And now, since we have split the only bucket that existed at the beginning of round 1, we also immediately enter round number 2, as you see in the counter here, and we are resetting the split next pointer to the first entry, to the first of our buckets here. Okay, so now assume that we have even more insertions into our table and therefore into the associated index. So now we have again to split the bucket that our pointer is referencing. So now we have one bucket that is associated with hash values ending in 0, 0, and one bucket that is associated with hash values ending in 1, 0. All right. So we are still in round 2. We are now pointing to the last bucket that existed at the beginning of the round here. And after we split that one as well, we are resetting the counter again, and we are entering round number 3. So now we have 4 buckets that are associated with the 4 possible value combinations of the 2 last bits of the hash function. Okay, and now we can continue this, and we can split the first bucket here and the second bucket here, and so on. But the principle is the one that is summarized here. So if we want to insert something into one of those linear indexes, then first of all, we calculate again the hash value for the new entry to insert. And then we add this entry on the associated page, or if that page is full, we might have to introduce an overflow page, hoping, of course, that this overflow page will be eliminated relatively soon. Now, if some kind of trigger condition is satisfied, we decide to split the next bucket. We have no choice about which bucket we can split. We can only split the bucket that our next split pointer is referencing. And there is some flexibility in how we can choose that trigger condition. For instance, we can say that we trigger a bucket split whenever we had a certain number of insertions, or we could say that we trigger a bucket split if we have one page overflowing. But as discussed, it is very important to understand that even if one page is overflowing somewhere, this is probably not the page that we will be immediately splitting. So only over time will we get rid of those overflow pages if we continue splitting buckets. All right. So those splits will eventually eliminate overflow pages. And as we have discussed, the splitting generally proceeds in rounds. So if we have split all the buckets that existed at the beginning of a round, then the current round ends. And if the current round ends, then as we have seen in that little illustration, we reset the pointer to the next bucket to split to the first of the current buckets. All right. And the bucket that we split next, that is always the one that we are pointing to. If we add a new page, then we generally redistribute the entries from the split bucket, and we do so by considering one more bit from the associated hash function. So that is the principle behind linear hashing. And if we compare the pros and cons, then the nice thing about linear hashing is that it avoids the directory, so we don't have any expensive directory doubling. It has the drawback that it might temporarily admit overflow pages, and it sometimes may split pages that are empty or near empty, which means that I probably use up more space than is necessary. So those are a couple of drawbacks, but nevertheless, this is a pretty convenient hashing method. Now, we have discussed about a couple of optimizations in the context of tree indexes, and in principle, we can use all of those optimizations for hash indexes as well. For instance, if we have many entries for the same search key value, then we can store that key value once, followed by a list of references. So we have also that possibility for tree indexes. The advantage is that I store less redundant data. A disadvantage is that I might transform a fixed length entry into a variable length entry, and that means I would have to store additional metadata on my page in order to save where this list starts and where this list ends, for instance. Also, so far we have assumed that my data entries in the index, that they essentially store references to the actual data. But that is not necessary. I can in principle also store the actual data directly. Now, this is what we also call a clustered index. As long as you don't want to store duplicates of your data, which you generally avoid, it means that you can only have one of those indexes per table, because that index is essentially merged with the table data, right? So that makes retrieval more efficient because you save one lookup, and also you are guaranteed that the data with the same index search key is stored close together. Otherwise, the references might actually point to very different areas of your data set. In general, even if you don't store the data directly in the index, it will help you if your data is sorted according to the index search key, because that means things that are stored close together in the index will also be stored together in the original data set. And that makes it quite efficient to retrieve the associated data with a few page accesses. So if the order of the data is consistent with the index search key, then that is also called a clustered index in general. And here retrieval is also more efficient in general than if that is not the case. So those are just a couple of optimizations in the context of hash indexes, and they're essentially the same optimizations that you can apply for tree indexes. Now, a little word on how you can use those indexes in Postgres, and I'm going to show a quick example about that next time. So in Postgres, you can generally choose the type of index that is generated. By default, it will generate B trees, but you can specify explicitly which type of index you wanted to generate. So with the syntax here, create index, then the name of the index, then on the table that the index refers to. And if you insert here using method, the method can be, for instance, B tree or hash or other methods that are discussed in the documentation. Then you can choose what type of index you generate. And again, here between parentheses, you can specify the columns that your index should refer to. So if you want a composite index, you can specify multiple columns here. All right. And now we have already reached the end of the lecture time. So I'm gonna show you quickly how to use those indexes in Postgres next time. The next homework will focus on indexes. So I encourage you to revise the indexing material a little bit over the weekend. And otherwise, have a great day and see you next week.